Okay, today the discussion will be on shapes of atomic orbitals. So we all know what is atomic orbitals. We have discussed in our previous class also. S, P, D, F. So these are the orbitals, atomic orbitals. S, P, D, F, we have discussed about that before also. So for today we are going to discuss about these three orbitals, S, P, D, shape of SPD orbitals. F onwards the shapes become more complicated, so we are going to discuss whatever is given in your textbook. Okay, so this psi, okay, we have discussed this psi, okay, in Schrodinger equation also. So this psi gives the probability of finding an electron, okay, this psi. So when this psi, the function this psi, okay, as a function of radius is plotted against this radius, okay, of atomic of an atom, we get this graph, okay, psi versus r. We get this graph, okay, as shown here. So I've already drawn this graph, okay, in order to save times. So this psi gives the probability of finding an electron. So this graph, okay, the first graph is an example of 1s orbital, okay. So 1s orbital has n principal quantum number 1, okay, and L is equal to 0. In this case, okay, as we have seen from this graph, okay, these red lines, okay, is moving away, okay, like this in a curved shape, okay. So this graph means that if we move away from the nucleus, okay, or if we move away, okay, from the nucleus, okay, or if we move away, okay, that means the radius will increase, okay, the radius will increase, and then the probability of finding the electron will decrease, okay. That means if we move far away, that probability will decrease, okay. For 2s orbitals, okay, the graph follows like this, okay. If we move away, also the probability of finding the electron decreases, okay. So the probability of finding the electron is increases near the nucleus, okay, near the nucleus. So we have learned seen about this psi. Now let's see about psi square, okay. So in that Schrodinger equation, that psi square is given, okay. So this will give the most probable value, okay, of finding the electron, okay, psi square, as a function of radius. So likewise, as we move away from the nucleus, the probability of finding the electron decreases. For 2s orbitals, as we move away from the nucleus, okay, the probability decreases till it touches 0, okay, 0, and then after some time it increases and then decreases, okay. So if we move far away from the nucleus for 2s orbitals, okay, the probability of finding the electron decreases and it reaches a minimum or 0, and then it reaches a maximum or maxima, okay, and then decreases, okay. So we call this point where it reaches 0, okay. That means probability of finding the electron is 0. So this point we call it as nodal surface. So we call this as nodes or nodal surface. So for ns orbitals, okay, the nodes is given by n minus 1. That means principal quantum number minus 1. Okay, so this formula will, or this relation will give the number of nodes, okay, in a specific orbitals. So for 1s, okay, since only one principal quantum number is there, so no nodes is present in 1s orbital. It will be 0. 2s, okay, and minus 1, it will be 1, okay, and 3s, it will be 2, okay, 3 minus 1, 2, and so on. So the number of nodes, okay, for 1s is 0, 2s 1, we have already seen here, and 3s will be 2, 4s will be 3, and so on. So this density, okay, this graph, through this graph, okay, we can come to the conclusion that we can draw a charge cloud diagrams, okay, for better understanding of the shape of atomic orbitals. So this is the probability density diagram, okay. So the probability of finding the electron near the nucleus, okay, near the nucleus is maximum, okay. So near the nucleus it's maximum, okay, and then decreases, okay, if we move away from the nucleus, okay. So this diagram shows the probability, okay, of finding the electron, okay. Next, for 2s, so the probability of finding the electron is highest near the nucleus, and then decreases if you move away from the nucleus, and it reaches a minimum, okay, or minima to 0, okay. So we call this as nodal surface. So you can see a space, okay, a clear space around this, okay, in a circular form. So this space represent the nodes or nodal surface, and then the electron density increases, okay. After this it increases, okay, reaches a maxima, and then decreases, okay. If you move further away, it will decrease. So these electrons can be anywhere, okay, in the space, okay. So the probability of finding this electron can reach till infinity, okay. That means it can cover a very infinite space, okay. So if you have to draw the shape, it will be impossible, okay, to draw that shape, okay. That will become a very big shape, okay. But considering 90%, okay, 90% of the electron density, okay, in the or in around the nucleus, okay, where maximum probability of finding the electron is 90%, okay. So around that probability of maximum, okay, finding maximum number of finding the density of electrons, we drew a circle, okay, circle, and represented it like this, okay. Actually the shape is spherical, okay, for s orbital, okay. The shape is spherical, that means like a ball. So it look like this, like a ball, okay. This shiny things also appear here to show it like more like a 3D structure. Okay, so in actual it is 3D in spherical shape. So with this we draw a diagram, okay, or a spherical or a circle. Okay, so this is known as boundary surface diagram. Okay, the first one is the probability density. So these boundary surface diagrams give the shape of the orbitals, and we come to the conclusion that as orbital is spherical in shape. So for next we come to the boundary surface diagrams of 2p, okay, or we can say p orbitals. So p has 3 different orbitals. 2px, 2py, and 2pz. So it has 3 orbitals, okay, and they are all dumbbell shape, okay, dumbbell shape, or the dumbbell we use in gym, okay. So they look like dumbbell shape, and it has 2 lobes, okay. One look like this and the other look like this, okay, 2 lobes. So why there are 3 different 2p orbitals? They all look the same, okay, having the same symmetry, shape, structure, okay, but they differ in their orientation, okay, along the x-axis, y-axis, or z-axis, okay. So through, because they have different orientations, okay, they comes in different shapes. So 2p has 3 different orbitals: 2px, 2py, and 2pz. So the probability of finding the electron, okay, along this, where these 2 lobes meets, 2 lobes meet, okay, this axis is 0, okay. The probability of finding the electron is 0, okay, where these 2 lobes meets, okay, along this axis. Let's look at the diagram for 2px, okay, px. So these lobes comes along the axis, x-axis, okay, x-axis, and the probability of finding the electron will be 0 along this axis, okay, along this axis, okay. 2py, for 2py it will come along the y-axis, okay, as shown in the diagram, and then for 2pz along z-axis, okay. So we call this surface, okay, as radial surface, okay, radial surface, because they are uniformly distributed, okay, in 3 dimensions, okay, in spherical shape, okay. Now for this case, okay, since it is along the x-axis, okay, the z-axis and y-axis, we can draw a plane, okay. So we call this plane as angular nodal surface or nodal plane. So for this 2px there is one nodal plane, okay, and here also there will be one nodal plane. So in this plane, okay, along this plane the probability of finding the electron will be 0. For this case the plane will be in this case, okay, z and x-axis. Along z and x-axis, the plane will be along the z and x-axis. For 2pz, the plane will be along x and y-axis. Okay, plane means like this paper. Okay, like this paper. So in this case, there will be no radial surface. Okay, as in s orbital. Okay, for p orbital, no radial surface will be present. Radial surface is absent for p orbitals. So we have discussed about s and p orbitals. Now we come to d orbitals. So d has 5 orbitals. Okay, dxy, dxz, dyz, dx square, y square, and then dz square. 5 orbitals. Okay, like before, they differ in their orientation. Okay, along x-axis, y-axis, or z-axis. For dxy, okay, in this case it's a bit different than the p orbitals. For d orbitals, okay, dxy, so these lobes, okay, are double dumbbell. Okay, means 2 dumbbells are there. Okay, double dumbbell, so they will point along in between, in between x and y axis. Okay, x, y, so they are in between this x and y and along z. Okay, don't get confused. And for this case also, dxz, so it will be in between. Okay, the lobes will be in between the x and z axis. So x, okay, in between x and z axis and along y axis. Okay, now for the next one also, dyz, so in between y and z, so y and z. Okay, so in between y and z and along x-axis. Okay, next one, dx square, y square. For this case, okay, it will be along x-axis and y-axis. Okay, that's why we are giving square. So y-axis, x-axis. Okay, now the last one is dz square. So z square means it will be along z-axis. Okay, and it is given by a circular kind of diagram. Okay, here. So this is the boundary surface diagrams of the 5 3D orbitals. So for this case, radial surface is present. Okay, as we have discussed, for p orbital radial surface is absent. For this case, radial surface is present. And for this case, nodal planes or angular nodal planes. Okay, so for d orbitals, 2 nodal plane is present. Okay, we can draw one nodal plane here and the other nodal plane here. So for d orbitals, 2 nodal planes will be present for d orbitals. Okay, we won't discuss further about this. So we have discussed about the nodes. Okay, so total number of nodes n minus 1 will be is equal to angular nodes. This angular nodes is this one. Okay, nodal planes. We call it nodal plane also, or nodal planes. So this angular nodes is represented by L, okay, plus radial nodes. So radial nodes is n minus 1 minus this is L, okay, and this is 1. Total nodes will be is equal to angular nodes plus radial nodes. Oh, if this seems confusing, you can just write n minus 1, okay, principal quantum number minus 1, okay. So this will give the number of nodes present in those, okay, orbitals, 2s, 3s, like that, okay. And one more thing, one s orbital is smaller than 2s orbital, okay. So and then 3s orbital will be larger than 2s orbital. Similarly, 4s orbital will be greater than 3s orbital. Okay, so this will be larger than this one, and okay, this orbital will be larger than this one, then this will be larger than this one, and so on. So accordingly the size will differ, okay, in this manner. So with this we come to the end of these shapes of, okay, of atomic orbitals.